Okay, guys. So let's sort of set the stage for where we're at. We are going to review a little bit as we go, and then we're going to dig into acid and base chemistry. Guys, understand this is when school changed last year. I actually walked into class when I came back in August, and my cabinets were full of the last test that you guys took. And it was the test, it was the rate test. No, it wasn't. It was the one before that. Guys, when we got back, we were starting into acid and base chemistry, and you did all of this online. So I understand you're at a huge deficit. We'll go slow. We'll see how this goes. But guys, with that said, let's put this in context. So guys, chapter 4 is all about aqueous chemistry, which we understand means in water. And importantly, it involves ions. We'll come back to that in a minute. So guys, previously we talked about precipitation reactions. We're done with that. Today, or maybe today and next time, we're going to talk about acid-base chemistry. Then we're going to do redox reactions. Then guys, when we're done with redox chemistry, we'll spend a short day talking about titrations, and then we'll be all done for the unit. But guys, with that said, in order to really understand acid-base chemistry, we need to jump back up here and talk about ions in solution. So guys, a little primer. Let's make sure we're clear. So guys, when we talk about things that dissolve in water, we have electrolytes and we have non-electrolytes. What's the difference? Electrolytes and non-electrolytes. What do electrolytes do that non-electrolytes don't? Break into ions. Now guys, understand that non-electrolytes, like alcohols, like sugar, they dissolve in water. What they don't do is ionize. So we've got electrolytes that dissolve and ionize. We've got non-electrolytes that dissolve but don't ionize. You good on that? Okay. Then guys, we take electrolytes and we break them into two types. We've got strong electrolytes and we've got weak electrolytes. What do strong electrolytes do? Break apart completely into ions. What about weak electrolytes? What do? Break apart partially into ions, and instead of going to completion, they reach a state that we call what? Equilibrium. Okay, so guys, this becomes our transitional thought. In the same way that we have strong and weak electrolytes, and guys, pause for a minute. Strong and weak electrolytes. Strong break apart completely, weak do not. You're going to find out we also have strong and weak acids. And guys, understand that when we say strong acids, it doesn't mean it hurts you a lot. What does the word strong mean in chemistry? Breaks apart completely. That's all that it means here as well. Because guys, you're going to find out that there, for example, are bases that are crazy good bases, but they're not strong bases. They are really good bases, but they are not strong bases. So guys, I bring that up only to draw your attention to the fact that this gets a little bit weird. And when we start talking about acids, if you think strong means dangerous and weak means not dangerous, that's going to get you in trouble. So guys, remember the definitions of strong and weak as we get going. So, with that said, let's talk about acids. I would actually encourage you to scratch these things down in your notes, but here we go. So guys, when we talk about acids, I know that you hear about acids and things start running through your head about what makes something an acid. I'm going to try to ask these things as questions, but I frankly don't know how much you know, so we'll see how it goes. So guys, fundamentally, what makes something an acid? That's it. Guys, that's all there is to it. It gives away hydrogen. That's it. That's all an acid is a substance that gives away hydrogen in water. Uh-oh. But guys, please be careful. It does not give away hydrogen atom. It gives away hydrogen ion. And by now you should be comfortable with the idea that atoms and ions are completely different things. Sodium atom is a shiny explosive metal. Sodium ion is dissolved in water and we eat it and drink it all the time. So guys, the ionic forms and the metallic forms, the elemental forms, are completely different. So guys, over here on the right-hand side of your notes, please draw your best picture of a hydrogen ion. Over on the right, draw yourself a picture of a hydrogen ion. You guys done? Here's what my picture looks like. Done. It's a proton. Ooh. And then put a P in it? It is important. No, and it is, yes, but it's important to understand that it's a proton. So guys, understand that when we talk about acids being, all right, this mask is killing me. So guys, when we talk about these things giving away hydrogens, hydrogen ions, are these any good? It tastes funny. All right, I'm going to try this. At least it stays put on my face. This is my first time in a tiger mask. What do you think? Thank you. That's really sad. All right. So, guys, please be clear on this idea that when we talk about hydrogen ions, what we're talking about is protons. And if you're not making the connection, if we look up here at fundamentally what a hydrogen atom is, a hydrogen atom has one proton and one electron. So literally a hydrogen atom is just a proton with an electron doing its 1s orbital thing, right? But when this becomes a hydrogen ion, the electron is gone and we're just left with a proton. So literally, guys, all acids do is they donate protons. You good on the idea? Okay. So then the question becomes, what does that do to water? Well, guys, fundamentally, it increases the concentration of hydrogen ion in the water. All right. So, guys, what I'd like to do then is we're going to take this idea of hydrogen ions and we understand that that's what acids do, but we're going to drill into this a little more deeply. You're going to find out that when we talk about acids, we start to classify, or not quantify, but we describe acids with terms like this. So when we talk about a monoprotic acid, guys, tease that word apart and talk to me about what it means. Well, mono means one. What about protic? Well, that's proton, but wait a minute, get the connection? That hydrogen ions are protons. There's the connection. So when we describe an acid as being monoprotic, that simply means that this acid releases one hydrogen ion into solution. An example of that would be something like our good friend hydrochloric acid. When that thing breaks apart into solution, it forms hydrogen ions and chloride ions. So guys, here's what I'd like you to do then. Off to the left, not to the right. Off to the right in your notes, draw yourself a beaker. And let's make this 1 molar HCl. Matthew brought this up the other day when we were drawing pictures. Do we include the water? And guys, the answer is not yet. So guys, if you have a 1 molar HCl solution, please draw a picture, draw a representation of what is in 1 molar HCl. What's floating around in there? You good? So let's talk. Is there any HCl in our solution of HCl? No. You may remember, maybe you're starting to connect this. Guys, HCl is a strong acid. Because it's a strong acid, it completely protonates in water. So guys, this thing completely breaks into hydrogen ions and chloride ions like so. By the way, guys, what is HCl before we put it in water and make an acid? It's a gas. Did we talk about that? All of the strong acids are actually gases before we dissolve them in water. So it goes like so. But guys, here's the interesting thought. Don't miss this. This is actually technically incorrect. This is actually, and this is a little bit of a stretch. It's going back to last year. But guys, we need to talk about this. So when HCl goes into water, it does break into hydrogen ion and it does break into chloride ion, but now we need to talk about what actually happens. Write this in with me. Guys, what actually happens is this. Can you tell that that's plus H2O, even though it got smushed together? Guys, what actually happens is this. The hydrogen ion does not float freely in solution. The hydrogen ion actually grabs a hold of a water molecule, and what are the chances you remember what that turns into? Do you remember? Yeah, good, okay. Yeah, this turns into H3O plus, which is called the hydronium ion. So guys, in fact, there is no free hydrogen in an acidic solution. All of the hydrogen ions actually go and hook up with water molecules, and they form H3O ion that we call hydronium ion. So guys, if you spill acid on your arm and you're going, the acid's burning me. No, it's not. Actually, what's burning you is the hydronium ion. That's where the hydrogen ion goes. And so this is like the active ingredient in acids, because all the hydrogen ion actually goes to form hydronium ion. Is that starting to come back to you a little bit? Donnie, you okay? Just scratching, or is that okay? Do you guys remember any of that from last year? Little bit? Okay. All right. So guys, with that said, come on. With that said, let's now talk about what are called polyprotic acids. So guys, as you might imagine, a polyprotic acid is an acid that... yeah, please.
So on the last one, with chlorine.
Hold on. Yeah.
So chlorine bonds to itself.
So be careful. Yes, chlor...
Not when it's dissolved, right?
So I'm going to pick at words. You're absolutely right that chlorine bonds to itself. Let's talk about why. So if you draw the Lewis dot structure for chlorine, it looks like this. Okay? And so chlorine is very electronegative, and it's missing an electron, and it's so electron hungry that it will actually bond with another chlorine, and it becomes a diatomic. But now watch this. This is hydrochloric acid. If we draw the Lewis dot structure for this, here's our chlorine, and then hydrogen ion is bonded there. When this breaks apart, hydrogen ion loses its electron, donating that electron to the chlorine. So this is no longer chlorine, it is now chloride. And chloride as an ion has its valence shell satisfied with the electron that came from the hydrogen. Because this thing is satisfied, it is no longer electron hungry, and it doesn't become diatomic. Does that make sense? So, what does that look like, just quick and dirty? It looks like this. We understand that that is a chloride ion, and the only way that this can exist is dissolved in water, but it's been stabilized with that extra electron, and so it doesn't become diatomic. Is that okay? You guys good? Okay. So guys, let's jump down again then to this idea of polyprotic. So guys, you probably have picked up on this. Polyprotic obviously means that it gives away multiple hydrogens. The thing that you need to understand, guys, is that these releasings of hydrogens become progressively weaker. Let me show you what I'm talking about. Write this down with me, gang. This is the only strong polyprotic acid. There are 7 strong acids. Only one of them is polyprotic. What are the chances you know the name of this? Sulfuric acid. Guys, this is battery acid. So, when this thing dissolves in water, guys, when this thing goes into water, it protonates, producing hydrogen ion, and then HSO4, which is actually called bisulfate. But guys, it doesn't stop there. This bisulfate ion still contains another hydrogen, and it can release it. And when it does, it produces another proton, and it produces sulfate ion. But guys, here's the difference. Only the first step is strong. The second step reaches equilibrium. So now, guys, we're going to play the same game. Draw yourself a beaker now down by this. And guys, if you have 1 molar sulfuric acid, what's in the beaker? Don't include the water. Don't include the water. What's in the beaker? Draw yourself a picture. You okay? So guys, let's talk about it. In our beaker of sulfuric acid, is there any H2SO4? No. This is all completely broken apart. Into what? Well, it's broken into this and this. But now, guys, let's continue. What then happens to the bisulfate ion? Will we have any of this in water? We will. Because, guys, some of this breaks apart, but not all of it breaks apart. So some of this breaks apart, making this and this, but we still have some of that left. So, guys, in solution, we definitely have hydrogen ion. In addition to that, we have some HSO4 minus, but some of that breaks apart into more hydrogen ion and sulfate ion, SO4 2 minus. So guys, that is what a solution of sulfuric acid contains. Does that make sense? Okay, now do this. So guys, let me rewrite this so you can see it. So H2SO4, is that a strong acid or a weak acid? Now hold on. Guys, wait. Remember, what does strong mean it does? Completely breaks apart. What does weak do? Partially breaks apart. So guys, H2SO4, does it completely or partially break apart? Completely. Guys, there's none of it in solution. Don't miss this, guys. Don't miss this. This is a strong acid. It completely breaks apart, and there's none of it in solution. Does that make sense? But now, guys, what about HSO4? Strong acid or weak acid? That is a weak acid because some of it does break apart, but then it goes backwards. Just a second. So, guys, it's critical you understand the distinction. This completely breaks apart, strong acid. This partially breaks apart, making it a weak acid. Does that make sense? Matthew, go ahead. Oh, gosh, I'm sorry. Oh, is that why you guys were confused? Do we need to say that again, or can we think past my mistake? So, guys, this should have been H2SO4 strong acid, and then HSO4 minus weak acid. Guys, you understand the idea? Go ahead, Braden. Hold on. Oh, good question. So, Braden's question is really good, and let's talk about this. So, guys, previously we discussed the idea that we don't have any hydrogen ion floating around in solution. So, guys, where does this hydrogen ion actually go? It hooks up with water and it turns into hydronium ion. So, Braden, to your question, but guys, this is to all of you. When we talk about what acids do, we allow ourselves to just do this. But we actually understand that every one of these hooks up with a water and turns into that. So sometimes, for simplicity's sake, we'll just write it this way with the understanding that it's actually doing this. Great question. Say that again. Correct. So anytime a hydrogen ion goes into solution, it grabs a hold of a water and it turns into hydronium. Whether we choose to represent that or not, we'll do strategically, but that's actually what always happens. Yep. You guys good? Monopolyprotic, weak, strong. Sorry for that little confusion. Are we good? I think I hate this mask as much as my other one. Does it? You want to trade? Because then we'd both die. Okay. The only advantage to mine over yours is mine smells like coffee now. Okay, you guys good? We're all right? Okay. Oh my gosh. I forget. Never touch my screen or my mouse. Okay, so we were here. We're good with all of that. Clean that up. And guys, what I want to do then is I want to introduce you or bring you to these ideas by bringing... We said Susie, right? Susie? Isn't that her name? We're going to bring Susie into the conversation. All right, so let's let Susie take a shot at this.
An acid is a substance that produces hydrogen ions when dissolved in water.
So guys, we're going to watch this twice.
Hydrogen chloride is an example of a common and important acid. When hydrogen chloride gas dissolves in water, it forms hydrochloric acid. Hydrogen chloride is very soluble in water and is completely dissociated. It is therefore a strong electrolyte. Nitric acid is another common strong acid. Upon dissolving in water, nitric acid completely ionizes to form an acidic solution. Like hydrogen chloride, nitric acid is a strong electrolyte. Acetic acid is the major ingredient of vinegar. When acetic acid is added to water, it does not completely ionize. It is therefore termed a weak electrolyte or weak acid.
Okay, so let's try this again. So going back to HCl.
An acid is a substance that produces hydrogen ions when dissolved in water. Hydrogen chloride is an example of a common and important acid. When hydrogen chloride gas dissolves in water, it forms
Okay, so let's stop right there. So when HCl dissolves in water, it breaks into hydrogen ions white, chloride ions green. But guys, to be clear, what's missing from this picture? Is this really what's in solution? It is not. What's missing? The water. So guys, what actually happens is this. We've got an oxygen with 2 hydrogen atoms, and this actually forms hydronium ion. But when that hydrogen turns into hydronium ion, do these dudes ever get back together? They do not. How do we know they won't? Because HCl is a strong acid. Does that make sense? Okay. So guys, moving along then, let's now look at nitric acid. How do I do this? Not like that. So guys, moving along and looking at nitric acid then.
Hydrogen chloride associated. Acidic solution.
Again, the idea, these split up. Can you see that hydrogen actually in hydronium as well? Will they come back together? They do not. It's a strong acid. Then
Like
moving along to vinegar.
It is therefore termed a weak electrolyte.
So this breaks apart. Again, this is actually attached to a water molecule forming hydronium ion. But guys, what's the difference now? These guys will reassociate. And guys, understand, it isn't necessarily the hydrogen that it lost that it gains back. There's billions of these in solution. The idea is that this is actually a pretty good base. And because it's a good base, it will pull that hydrogen back from hydronium and it'll turn back into the original acetic acid molecule, making this a weak acid. Do you see the distinction? Anything there you want to talk about? Please, go ahead, Donnie. Ooh. Say it. Begins with the C? Yeah. I'm looking at the clock and I'm looking at what we're going to do. Can I let that be a bookmark for next time? But let's say that. Guys, please don't miss this. This is huge, but we're not going to get to it today. But Donnie's exactly right. Let's say this important thing again. So remember what we said. So when this thing loses a hydrogen, this will go back. This acts as a base and it pulls that hydrogen back. The name of that is a conjugate base. But what you said is exactly right. The weak acids form negative ions that are pretty good bases. We call them conjugate bases, and that pulls the ion back and it functions as a base. And so guys, we're not going to get to this today, but we will talk about it Thursday. How are we doing on weak and strong acids? You guys good? Okay. So guys, similar conversation then about bases. So here we go. Similar conversation, it's just the hydrogens are moving in the other direction. So guys, when we talk about bases, we are talking about substances that accept hydrogen ions. But guys, this is the interesting contrast. You ready? When we talked about acids, link these two ideas together. We said an acid gives away hydrogens and increases the concentration of hydrogen in solution. You guys, check this out. Bases accept hydrogens and they increase the concentration of OH in solution. Do you see the distinction? Acids give away hydrogens, hydrogen concentration goes up. Bases take in hydrogens, and the OH concentration goes up. What on earth is going on? Well, guys, draw a picture with me. This is a water molecule. Hydrogen, oxygen, hydrogen. So guys, check this out. What do bases do? They steal hydrogens. So guys, if a base steals a hydrogen from water, what's left over? OH. Do you see it? So guys, that's how this makes sense. that bases function by taking hydrogens away. Many times it's taking hydrogen away from water, and when that happens, what's left over is hydroxide, and the hydroxide concentration goes up. Now guys, with that said, we now need to talk about the types of bases. So, two types, not mono and poly. Guys, the two types of bases are, first of all, the metal hydroxide bases. So guys, this should make your ears tickle a little bit. The group 1 and heavy group 2 metals hydroxides. So group 1 and heavy group 2, what does that make these guys that we're talking about? The strong bases. So for example, let's take potassium hydroxide. When you put potassium hydroxide in water, you get potassium and you get hydroxide, and there's our hydroxide ion. So guys, the strong bases don't have to make hydroxide by stealing hydrogens from water. The strong bases bring hydroxide to the table, and when they dissolve, they just dump hydroxide into water. But then guys, we've got another, and these are the strong bases. Then we've got another type of base. These are what are called the non-hydroxide bases. The only one that you need to know right now is ammonia. So guys, here's what I want you to do. Complete that balanced equation. What are the products? So guys, let's take a swing at this. We've already identified that NH3 is a base. That means it's going to take in hydrogen. So when NH3 takes in a hydrogen, what does it become? NH4 plus. The proton that it takes in is a positive charge, so that becomes NH4 plus, which you will eventually memorize to be ammonium. And when that happens, the hydrogen comes off of the water, and that produces hydroxide, and that then is our other product, and there's our OH. But guys, here's the thing you need to know. These are the weak bases. These are not the strong bases. These are the weak bases. So gang, if that's a weak base, why is this balanced equation wrong? Yeah, it goes both ways. This reaches equilibrium. It does not fully dissociate. So guys, that being the case, draw yourself the beaker again. What is in a 1 molar, doesn't really matter the concentration. What is in a 1 molar ammonia solution? By the way, guys, NH3 is ammonia. What's in the bucket? So let's look. Do we have any NH3 still in the bucket? We do. Because this reaches equilibrium, not all of the NH3 is going to turn into NH4. So we do have NH3 in the bucket. But guys, every one of these NH3s that attacks water will turn into an NH4 and an OH. But in order for this to make any sense at all, we should include the water, because the water is the source of the OH. What do you think? You realize there's only one thing to do now. Go get Susie. All right, Susie, show us the magic. Here she comes.
Bases are substances that increase the concentration of hydroxide ion in water. Water-soluble ionic hydroxides, such as sodium hydroxide, potassium hydroxide, and calcium hydroxide, are among the most common bases. When sodium hydroxide is dissolved in water, it completely dissociates into sodium and hydroxide ions. Because sodium hydroxide is completely ionized in solution, it is referred to as a strong base.
Does that sit okay with you? Sodium's hydroxide, strong, never comes back together? Okay.
It is also, of course, a strong electrolyte.
And guys, make sure you're making that connection. Strong base is a strong electrolyte because they mean the same thing. Strong means completely breaks apart into ions.
Ammonia does not contain the hydroxide ion, but is basic in water. When gaseous ammonia dissolves in water, it reacts with water to form the...
Aha! So there's our OH. But what's going to happen when I hit play? They're going to go back together. Will they stay together? What's going to happen? But what's going to happen to that hydrogen at first? It'll get exchanged.
Ammonium and hydroxide
Yeah? Back and forth and back and forth.
ions. However, ammonia is a weak base. The equilibrium forming the hydroxide and ammonium ions lies largely to the left.
Good? Does that jive with what you thought it might be? Okay.
At any given time, most of the ammonia is in a non-ionized form.
There you have it. So, guys, this is where we're going to call it quits today. We understand bases and acids at a greater level. We've talked about this idea of hydronium ion, and we're beginning to get a sense of strong and weak characteristics of acids and bases. We're going to come back we'll come back on Thursday, and Donnie, the first thing we're going to talk about is conjugates. So we're going to go to conjugates, and we're going to talk about those. And then, guys, to wrap up the day on Thursday, we're going to look at some very specific acid-base reaction types that you're going to need to have a handle on. But, guys, for tonight, then, what we're going to do, the homework assignment is not very long. Let me read this to you. So it's 29, 30, 31, 33, 34, 35, 37, 39, and 41. So guys, with that said, we'll do 29, we'll do 30, do 31, we'll do 33. It's an interesting question. We'll also do 34. We'll do 35. Wow. We'll do 37. We'll stop there. So guys, we're going to take a break there. Hey guys, if you did not turn in your chapter 4 summaries, I forgot to call for them last time. Please put those in the basket. We will take a break at 10:10 and then we'll come back together.